I think I'm going to kind of do things out of sequence. Well, I don't want to skip the important stuff while no one's here. I got a feeling people will be filtering in. Whatever, it's recorded. Okay, so where are we at? We need to wrap up a little bit of our thermochemistry. So we're supposed to be familiar with doing delta H calculations. Those are pretty straightforward. We're going to practice a few of those today. But we have to prep you for lab today. And in lab, we're going to be doing ion systems, salts that are soluble in water, soluble or insoluble in water. We'll talk about that. We can discuss thermodynamics in the context of those experiments, though. So that's what we're going to do right now. We're going to just kind of try to shed the thermodynamic light on today's lab. So today's lab, you're going to be working with an insoluble salt, insoluble compounds. You'll work with two solutions that contain soluble salts. You'll combine them together, and at the end of the experiment, an insoluble precipitate will form. And it's going to get sucked to the bottom of your container, and you're going to pull it out. You'll probably weigh it. You'll dry it out, and then next week you'll come back and weigh it and see how much of it there was. In the context of that, we're going to just review real quickly what it is that causes something to be soluble or insoluble. And you can't read these words very well, but what I'm orating right now is basically what's up there. When we're dealing with salts in solution, we have to worry about forces in two different places. Last week we looked at those batteries, and we had to look at all kinds of different forces. Forces between the solid state and the dissolved state, and forces of the electrons tied to the atoms. In this case, it's a much simpler situation. We've already talked about this once. We've got the forces in the solid phase that act between the individually positively and negatively charged ions. And so that's actually what this picture is supposed to be up here. I've got 4 ions stacked on top of each other, and they're bound by their electrostatic forces. And again, we've got the forces between the solvated ions and the water dipoles. So these are ion-ion interactions, these are ion-dipole interactions. And the question of solubility is largely a function of which of these forces are stronger. But it's not entirely a function of which of those forces are stronger. There's one more thing that we have to consider, and that is entropy, the disorder of reaction. And it tends to be, I've said this before, that things going into solution create more disorder. You have two possible states for a system of matter. You can have it in a condensed solid phase, or you can have it dispersed through the solution. Well, when the phase is dispersed through the solution, when the substance is dispersed through the solution, there's more disorder in the substance. There's more ways that it can be dispersed through that solution. And so, entropically, we always kind of have this situation where the dissolving of the substance is favored by entropy. Okay, so 3 things we got to consider again: the ion-ion forces. Just call these forces. Ion-ion forces in the solid salt. Those will be in competition with the ion dipole forces in the dissolved state. And we have entropy favors the solution. Want to make a quick note on the next page. I'm going to switch from having drawn the individual waters as H2Os to just making them look like little V's. So the two-pronged end of the V is the H's, which is the positive end of the water dipole, and the one-pronged end of the V is the oxygen, which is the negative. So we've got a competition between these forces. I'm going to try to draw a couple of scenarios for you. I don't know if this is the best exact illustration, but I think it'll work. Supposed to be a graph of energy increasing here. Say we've got a situation, several different situations, but three different situations. One, we can have the case where the ion-ion forces in the solid are so strong that they overpower both the ion dipole and the entropy forces. In that case, your solid is not going to dissolve. It's going to stay bound in with those ion-ion forces because that will represent the lowest energy state for the salt to be in. In that case, our graph might look like this. We've got ion dipole forces that are smaller than the ion-ion forces. And we have an entropy component that delta S that still favors the dissolved state, but is not quite enough to make the total forces favoring the dissolved state outweigh the forces that are favoring the solid state. Okay, so this will represent an insoluble compound because the greatest forces are the forces that are favoring your solid phase. Another situation. We have that our ion-ion forces outweigh our ion dipole forces. But we might have that the entropy contribution happens to be large enough to make up the difference and to push the reaction in favor of the solubilization. So in this case, on the right-hand side, we've got the forces that favor solubilization, and they're greater than the total magnitude of the forces that favor the solid phase. In this case, what's going to happen is solubility is going to be favored, but you can think of the ion-ion and ion dipole forces as representing the electrical potentials. In this case, because the ion dipole forces are lower than the ion-ion forces, we actually go to higher electric potentials when we move into the solvated phase. So, you can think of the ion-ion forces and the ion dipole forces representing the delta H. So delta H, enthalpy, is just energy that's transferred in a reaction. Oftentimes in chemistry, what we're going to find is that the energy change in reactions are a function of changing electric potentials. And so what we have here is a situation where you go from really strong forces, low electric potentials in the solid, to higher electric potentials when that solid dissolves. So we're going up in electric potentials, but we're going down in total energy because that delta S term is large enough to outweigh those stronger forces in the solid. Anybody want to tell me whether or not they think that that reaction is going to be endothermic or exothermic? If we go to higher electric potentials, do we go down or up in electrical energy? Do we put energy in, electrical energy in? Endothermic. endothermic. We're going from stronger binding to weaker binding, so we're going up in electric potentials. That means that electric potential energy is going to have to be delivered to the system in order to get it into the solubility phase. Now, it'll still go up that hill because the magnitude of the delta S term is large enough that it kind of pushes it in that direction. So this is the case, this is a scenario that would give rise to an endothermic dissolution. Right? One other scenario. In this scenario, we've got our ion-ion forces of some particular magnitude, and they're outweighed by the ion dipole forces. Now, we always have that entropy favors the dissolution, generally. And so in that situation, all of the forces kind of drive the reaction towards the dissolved state. Heavily favored for the dissolved state. And because the ion dipole forces are stronger than the ion-ion forces in the solid, we move down in electric potential energies when we go into the dissolved state. And so this reaction, because we're going down in potential energy, is going to be excellent. So the three situations. In the case of insolubility, we have so much stronger ion-ion forces in the solid that even the sum of the ion dipole term and the delta S term cannot outweigh the ion-ion forces in the solid. That salt is going to be insoluble, it will not go into solution. Scenario number two, we have ion-ion forces that are stronger than ion dipole forces, but the magnitude of the delta S term that favors dissolution is large enough to push the total energy towards the dissolved state. In that case, we're going up in electric potential because the electric binding forces are actually weaker in the final state than they were in the initial state. And so we're going to release energy, we're going to release that take on energy, take on electric potential energy, and we'll have a dissolution process that is endothermic, absorbs energy. And then case number three, in that case, both the ion dipole terms and the delta S term, or the ion dipole term is large enough to outweigh the ion-ion term. We've got stronger binding with water than we have with salt, and we have the delta S term that favors that. So this reaction will proceed, and it will be exothermic because we are lower in our electrical potentials. Does that make sense? Okay. We're going to talk about this more next week, but I'll throw it at you one time right now. Wet your whistles or something. Prime your pumps. If we go, in this case, up in electric potential energy, where does that energy come from? It comes from whatever else is around us. We have salts that are endothermic. When you put them into solution, you feel that the outside of the container starts to get cold. Well, that's because in an endothermic reaction, in order to proceed, you've got to pull energy in from somewhere. And so, in an endothermic reaction, the environment, the surrounding environment, provides the energy needed to drive the reaction. And if energy is being sucked out of the environment and put into the system, you'll notice a temperature decrease in the environment. So, in the endothermic case, the temperature of the environment decreases. We call it the surroundings. In an exothermic case, the system releases energy. So we went from, in the exothermic case, we went to tighter binding in the final state than in the initial state, and so we lowered our electrical potentials. that electric potential energy is released in the form of photons or whatever else you get out of it, and that energy is absorbed by the surroundings. And so the temperature of the surroundings increases in the case of an exothermic reaction. Practice for what you guys are going to be doing today. And this is some practice with limiting reagents and stoichiometry as well. One of the cases of insoluble compounds are compounds where lead, Pb2+, is paired with counterions that have kind of high negative charges. It happens to be that if you take a lead 2+ ion and you stick it in solution with a phosphate PO4 3- ion, the 3- charge on that lead, the 3- charge on the phosphate and the 2+ charge on the lead are going to provide sufficient electrostatic interactions that they'll bind together and they'll form that insoluble precipitate because the binding is so tight between the 3+ and the 2+ charge. So the solid will form. Right here, what I've shown, you can't see it that well, but this is a solution of lead nitrate. I've got 3 moles of lead nitrate in there. Sorry, there's my drug user. I've got three moles of lead nitrate. So 3 Pb2+ ions, 6 NO3- ions. Nitrate, the NO3-, that's one of your really highly insoluble, negatively charged ions. And so this solution, this lead nitrate, is completely dissolved in solution. And that's why I've got those little V's, those are your water molecules, right? The negative end of the water pointing towards the positive ions, the positive end of the water towards the negative ions. So in that solution, everything is dispersed, everything is soluble. Over here, we got this solution. In this solution, I've got 3 moles of sodium phosphate. Sodium phosphate, phosphate is PO4 3-. It's got to have 3 sodium ions paired to it. But that's another solution that's completely soluble. Sodium ion, very soluble ion. It's got that 1+ charge. It prefers to stay dissolved in solution. Not very strong forces in the solid. So 3 moles of that equates to 9 sodium atoms, 9 sodium ions, 3 phosphate ions. Something's going to happen when I pour these together. What's going to happen is once these guys get mixed in the same container and a phosphate bumps into a lead, they're going to get stuck together like glue. They're going to form a solid. So, not the greatest image in the world. By the time you guys are out of here and I'm teaching this class the second time, the next set of students will get great images. So, life sucks, sorry. You pour these together. The lead ions, Pb2+, and the phosphate ions are going to pair together, but they do so in such a way that their charge is neutralized. If you got PO4 3- and you got Pb2+, the easiest ratios to combine those in, or the smallest ratios to combine those in such the charge is neutralized, is that you pair 2 phosphate ions with 3 lead ions, right? You got 3 Pb2+ charges for a total of 6 positive charges. You got 2 PO4 3- atoms for a total of 6 negative charges. In the solid, the neutrally charged solid, you'll have 3 lead ions and 2 phosphate ions. So you got your solid phase that forms down there. Now note that 3 units of lead nitrate were required to react with 2 units of sodium phosphate. So if you were to write the unbalanced equation, it would look like this. Sorry, that's not in one stream. But you take lead nitrate, lead, 2 nitrates, you have sodium phosphate, it's 3 sodiums paired with 1 PO4 3- ion. You go on to form Pb3 PO4 2, so that's 2 phosphates paired with 3 leads. And then your remainder is sodium nitrate. We already kind of know that we're going to need 3 units of this to combine with 2 units of that to get a balance of charge in the product, right? And so, combine 3 units of this with 2 units of that, you'll form 1 unit of this guy, and then you'll have, did I get this right? Yeah, 6 units of that, NaNO3, they get formed. And so the sodium and nitrate don't actually react. They stay in the same dissolved state as they were in their initial containers. So the lead and the sodium and the nitrate don't do anything. They stay dissolved as they were in their previous containers, but they're left dissolved in the final solution because they're still soluble. The lead phosphate dissolves. In the problem that I did, that I showed you, I put 3 moles of lead nitrate in solution with 3 moles of sodium phosphate. I only needed 2 moles of sodium phosphate to pair with 3 moles of lead nitrate. Yeah? So what's left over? Give you a hint. There's a single phosphate ion still floating around in solution here. And it's paired with 3 sodium ions, or sorry, there's a single phosphate ion and it's paired with 3 sodium ions. And so at the end of the day, you had the soluble product of this reaction, 6 moles of sodium nitrate, which stayed dissolved, but you also had unreacted reactant, which was that sodium phosphate. So left over in the solution and still dissolved by water, we have a net of 9 sodium ions. We have 1 phosphate ion, and we have 6 nitrate ions. So the point is that whatever doesn't precipitate will end up staying dissolved in the solution, and we have a case of limiting reactant. In this case, our lead nitrate was our limiting reactant because we didn't have enough lead nitrate to completely react with our sodium phosphate. It's the kind of problem that you very, very easily could see on an exam. going to switch gears here for a second, I hope. We're going to start reviewing for the exam now. Could do the review on Tuesday or Thursday, but I figure if we go over this now, then that means we're sending you home over the weekend with something to think about for exams. It appeared on last exam that not everyone made best use of the practice exam. We ended up doing the practice exam in class. Here's practice exam number 2. It's supposed to have answers. Let me see here. Yeah, it's got the answers. One of the things you absolutely must be able to do at exam time is calculate these oxidation numbers. So problem number 2 in this practice exam gives you a bunch of kind of really simple problems for practicing oxidation numbers. Let's just go over a couple of them real quick here. So F, we've got a compound, P2O3, phosphorus and oxygen. Who's most electronegative? Oxygen. How many electrons does oxygen want? 2. How many oxygens do we have? 3. That creates a demand for 6 electrons, right? Those 6 electrons are going to have to come from the 2 phosphoruses. And so each of those phosphoruses is going to be a 3+ oxidation state. Here's one, the carbon in the HCO3-. We have 3 oxygens, so that creates a demand for 6 electrons, yeah? Because this compound is negatively charged, that means that we've gotten an extra electron from somewhere, something besides the actual atoms that are in there. We've been able to pull an electron off of another species. And so that electron is going to go to oxygen first, because oxygen is the most electronegative. Now we've got demand for 5 electrons. But one of those electrons is going to come from that hydrogen. It's the least electronegative species there, right? So oxygen, one of the oxygen atoms pulls that electron off of the hydrogen. Now we've got a demand left for 4 electrons, right? Who's going to provide those 4 electrons? Carbon is the only one left. And so your carbon goes into a 4+ state when it gives away those 4 electrons that the oxygen wants. How about this? N in NH4+. For some reason, my brain just went. N and NH4+. So we've lost a valence electron from somewhere. That's why we're positively charged. And well, let's look at this a different way. Normally, if it was a zero charge part or substance, we would say that the nitrogen was more electronegative than the 4 hydrogens. And so the nitrogen would be able to gain 4 electrons and go into a 4- state, and the hydrogens would each go into a 1+ state. But we've lost that extra electron from somewhere, and so the nitrogen doesn't actually end up in a 4- state, it ends up in a 3- state. The hydrogens are always in a 1+ state, that's what your little chart says, it tells you the hydrogens are always going to give up those electrons and go to a 1+ state, so that puts your nitrogen at -3 instead of -4, as it would have been if it was just reacting with 4 hydrogens. We didn't have the fact that it was an ion to consider. Does that make sense? Okay. Practice these. There's a bunch of different compounds that you can work with. And there's the practice in your homeworks that will help you familiar as you. Let's go on to something more important.